we're going to talk about the immunity, and I'm going to talk about the agglutination reactions, neutralization reactions, complement fixation, and the fluorescent antibody techniques. So the agglutination reactions, just to make it very easy for you, is the reaction between antibody and the antigen, and they produce a visible result, which is like a clot. And our name for it is the agglutination reaction. So as you can see, antigen reacts from the antibody. And the purpose for this reaction is they are used to assess the presence of antibodies in a specimen by mixing it with the particulate antigens, or like liquid antigen. And awkward. All right. So I'm not going to talk about, like, you can read it. So very, very easy. You have the antigen. You have the epitopes on the surface of the antigen, which is going to react with the antibody. So you can use this reaction if you want to find antibody. So you can use a specific antigen, which is going to react with this antibody. Or in reverse, you can use the specific antibody to find an antigen in a specimen. And then the principle of the agglutination reaction is that diseases may be diagnosed by combining the patient's serum with the unknown with a known antigen. That's what I was talking about here.
What makes IgM the most efficient?
Because it can react with any antibody.
Okay.
So I'm going to talk about it later. In order to identify an antibody, you can use another antibody. And diseases can be diagnosed by rising titer, which is the antibody concentration in a serum, or you can do the seroconversion from no antibodies before the illness to the presence of antibodies. It's almost easy. Like you can take someone's blood and you can check it for the presence of the antibodies, so you can find out if your immune system can beat the illness. That's what it is. And there is two types of agglutination tests. It can be direct or indirect. For the direct agglutination reactions, we test patient's serum for the presence of antibodies against the large cellular antigens, for example, bacteria. And for the indirect agglutination, to test patient's serum for the presence of antibodies against soluble antigens. And the antibodies will then cause the visible agglutination. And here's the picture. So I'm just going to explain it very fast. We have 7 wells, and they all have the same amount of the antigen. But however, every well has an equal amount of antibodies. And so the proportion 1 to 160 is it's going to be the lowest proportion of antibodies that will cause the reaction with the antigen. And for the slide, you can see that there is agglutination because there were still enough antibodies to react with the antigen. And for this guy, it's a negative result, so there was no agglutination because there were no enough antibodies to react with the antigen. And the second part of the agglutination is going to be indirect agglutination. For this slide, you can see we were checking for the antibodies. So we have the layered beads which reacted with the antigen on the surface, and we put when particles are coated with the antigens, agglutination indicates the presence of the antibodies. So we were looking for the specific antibody, so we used the antigen, and when we put it in the serum, we could see that there is agglutination because there was a clot when the antibodies were reacted with the antigens. On the second picture, we were looking for the antigens. So we put latex beads with the antibodies on its surface to the serum, and we could see the agglutination reaction because there were a particular antigen in the serum. So they both positive tests, but they were checking one for the antibody and the other was for the antigen. And there is a specific type of the agglutination test, which is the hemagglutination test, which reactions involve agglutination reactions using test red blood cells. Just to make it very, very easy for you, there are some viruses that particularly like red blood cells. So when they're in the body and make red blood cells to clot to each other, which produce like glutination. Like you can see, because there is a clot of it. And later on, I'm going to say how people can prevent this clot. By using the neutralization reactions. In neutralization reactions, the harmful effects of a bacteria exotoxin, we already know what is it, or virus can be eliminated by a specific antibody. An antitoxin is an antibody produced in response to a bacterial exotoxin or a toxoid that neutralizes the exotoxin. And you can use this technique in the hemagglutination test because because the antitoxins are gonna neutralize the viruses that like the red blood cells. And here is the example of the neutralization reactions. So without the antitoxin, you have the toxin and you have the cell, and the cell is damaged by the toxin. But when you have the antibodies, they're gonna react with the toxin by neutralizing them, and so you can see that the cell is not damaged. And virus neutralization reactions. In a virus neutralization test, the presence of antibodies against the virus can be detected by the antibody's ability to prevent cytopathic, which we know the cell-damaging effects of viruses in a cell culture. And antibodies against certain viruses can be detected by their ability to interfere with viral hemagglutination in viral hemagglutination inhibition test. That's what I was talking about, that you can use the antitoxins in order to neutralize the exotoxin by the gram-positive bacteria. And this is the virus neutralization reactions. So we have the antibody, we have a virus, so the antibody is going to neutralize the virus, so the red blood cells is going to stay on the top. And the next reaction is going to be the complement fixation reaction, which is, first of all, the complement is an antibody that is produced by our immune system. And then complement fixation reactions are serological tests based on the depletion of a fixed amount of complement in the presence of antigen-antibody reaction. So it's also very easy. Complement fixation reactions, they're going to occur only when there is an antibody-antigen reaction going on. And it's good for detecting very small amounts of antibody when the amount of antibodies is too low to cause a precipitation of glutination reactions. And there are two steps. The first one is the complement fixation step, and the next one is the indicator step. So here's the example. You have the antigen on the top with the epitopes on it, and you have the complement. And you put it in the serum where there is antibodies against the antigen. And as you can see, those antibodies going to react with antigen, and the complement is going to be fixed, so it's not going to damage any cell. And when you add any red blood cells, and you add them with the antibody for these red blood cells, you can see that this guy is already fixed. So, and this one, the red blood cell is going to be attached to the antibody, so the complement is not going to damage this cell. But when you put the same antigen and complement in the serum without antibody, you can see that there is no fixation, and the complement is going to be just flowing around. And when you add red blood cells with antibody for these red blood cells, you can see that the antigen is going to flow away, and this complement, because it's not fixed, is going to damage the red blood cells. And the last type of the technique is going to be the fluorescent antibody techniques. They are use antibodies labeled with the fluorescent dyes. It's very simple as well. First you dye the antibody, and then you add this antibody in the serum with the antigens, and if they're going to react, you're going to see this reaction. It's just going to like power up. And so for the direct fluorescent antibody test, they are used to identify specific microorganisms, antigens, and for the indirect fluorescent antibodies test, they are used to demonstrate the presence of antibodies against a specific antigen serum. So this is just a direct fluorescent antibody test. They are directed antibodies directed against antigens on the surface of a specific microorganisms are labeled with the fluorescent dye. That's what I was saying. So you dye the antibody first, and here's the reaction. So you have your bacteria, then you dye the antibody for this bacteria. You add this antibody for the serum with the bacteria, and they're gonna club together. And so on the microscope you can see it's gonna be like flashing. And for the indirect fluorescent antibody, I'm not gonna read it. It's very simple as well. So in this case, you have antibody, and you have IgM. You have the antibody that can react with any antibody, and you have your organism, which is antigen, and they react with antibody. And in order to identify that antibody, you have to use another antibody. So I'm just gonna show you the picture. So you have your organism, you put antibodies, they're going to react with each other, and then you have to identify this antibody. So in order to identify it, you use another antibody, which is the immunoglobulin. It's called anti-human immune serum globulin. And you dye it, and then they're going to connect with each other, and you can see them under the microscope. So that's how you identify the antibody. And the last one is going to be the flow symmetry. It's a fluorescent activated cell sorter, can be used to detect, count, or separate cells labeled with the fluorescent antibodies. So you have a mixture of cells is treated to label cells that have certain antigens with fluorescent antibody markers. Then you have to, then the cells mixture leave the nozzle in the droplet, and there is the laser and the detector of this red light. The laser beam strikes each droplet, and then you can see there is an electrically charged metal plate, the negative and the positive. And so the positive, the positive cells, they're going to react with the negative charger, and the negative is going to be react with the positive. And that's how you can separate them.
Whatever you have.
Then we have together.
Okay, so I'm going to talk about the enzyme-linked immunosorbent assay, which is the ELISA, Western blotting, feature diagnostic, and therapeutic immunology. So ELISA is the most widely used group of tests known as enzyme. There are two basic methods, direct and the direct ELISA, which detects antigens, while indirect detects antibodies. Direct ELISA, this test is to detect the presence of drugs in urine testing. For this test, antibodies specific for the drug are absorbed to the well on the microtiter plate. When the patient's urine sample is added to the well, any of the drug that it contained would bind to the antibody and capture it. So this is just showing how the positive test would look like. So the test can be detected by adding the substrate for the linked enzyme. The visible color is produced by the enzyme reacting with its substrate. So pretty much what you see here is what's being added into the well, and it's reacting with the antigen. And if there's a color change, then it means that the test is positive. The indirect is used to screen blood for antibodies to HIV. If antibodies in the blood and virus in the well have attached to each other, they will remain in the well, then it would be a positive test. Positive tests consist of a sandwich or a virus, antibody, enzyme, like linked anti, which is HISG. And then that would be the positive test. Pretty much the same procedure. And if there's a color change, then it would be a positive, this person would be tested positive for HIV. And then the Western blotting is used to identify a specific protein in a mixture. When the specific protein is in an antibody, the technique is valuable in diagnostic disease. And pretty much this is the test that they did on Lyme disease.